Okay, let's take a look at how to conduct a chi-square contingency table example in Google Sheets. So this is going to differ from a goodness of fit because with a goodness of fit, we had a certain number of categories, more than two, and we were comparing the frequencies in those categories to a pre-prescribed distribution of frequencies. We basically had one variable that had more than two choices. So in my video for that, we looked at colors of M&Ms. So the one variable was color, and it had 6 choices for colors. In a contingency table question, we have 2 variables, and each of those 2 variables have multiple options, more than 2 options, or 2 or more. I'm sorry. So more than one, I should have said. So in this case, we have 2 variables. We have an age that we can see is being separated into 1, 2, 3, 4, 5 categories. So you have 5 different age categories. And then educational attainment is the second variable, i.e. how much schooling, right? How much education do they get? And that has 1, 2, 3, 4 categories. So we end up getting a 5x4 table of data. There's our contingency table. So you can recognize the contingency table versus a goodness of fit test because the contingency table will have your data categorized 2 ways. In the M&M example, they were just categorized by color. In this example, the data is categorized by both age and educational attainment. So there's our 2 different variables. Okay, so the first thing we're going to do is load this data into our spreadsheet of choice, right? Google Sheets or Excel. So copy the whole thing, Control-C or Command-C if you're on a Mac, paste it over here, which I've already done. I just put it, in a place where I have some room, and then I double-clicked to make all of the columns wide enough so I could read everything. I just made it look kind of as pretty as I could so we could all see it nicely. Do whatever you want to do on your end to, keep it looking nice or whatever. Okay, so we've got our data. Now let's go through some of the steps. So here's our data. We're testing at a 1% level, and we're basically testing the question of, do the data show that educational attainment and age are dependent? Okay, what the heck is this dependent thing? Well, with the goodness of fit test, we're testing whether or not the distribution of percentages, proportions, matches some pre-prescribed distribution of proportions. In this case, we're pretty much asking kind of the same question, but we're really just asking if the proportions that we see in groups by one of the variables, if those differ by groups from the other variable. So in this case, does their age influence what kind of educational level they've attained? Now, obviously, if we were looking at age groups, from like less than 18 years old and then greater than that, then of course you're going to see an influence because you can't, complete high school for most people until you're 18. You obviously can't do years of college until you're over a certain age. So you have to make sure in this case, the lowest age bracket we had was 25. So everybody in all of these age brackets was old enough to have attained the highest level of educational attainment in our brackets, completed 4 or more years of college on a kind of standard typical route, right? A typical college student, if you went, and this is in the United States, if you went through all 12 years of high school, you should be 18 when you graduate. Some people graduate at 17, but usually 18. And then, of course, 4 more years of college. If you don't take any time off, you'd be done by the age of 22. So starting at the age of 25 gives you that 3-year buffer to take care of people who even take a year off or those kinds of things, or graduate from high school a year later, and so on and so forth. So you're making sure that that kind of age difference doesn't matter. And now we're just looking at how much older they are above 25, if that has some sort of impact. So Null is always that there is no difference. So in this case, we're saying educational attainment and age group are independent, meaning there's no difference from one group to the next. If these two variables are independent, one doesn't influence the other. Your age has no bearing whatsoever on how much schooling you've had. Okay? Whereas the alternative, same thing, these two variables, educational attainment and age group, are dependent. So these are going to be some of the easiest hypotheses you'll ever figure out, because it's always just the two random variables are either independent for the null or dependent for the alternative. What does that mean? It means one of them influences the other, i.e. they're dependent, or there's no influence between the two. Okay, in this problem, we have, right, qualitative data. So we have for chi-square stuff. We're collected for, how many variables, right? This time we have two variables, age and educational level, and they are taken from one sample, one big group of people. Which of the following assumptions? Well, they're pretty much the exact same assumptions that we had with the goodness of fit test, that in order for our sample to, not mess with the independence of the population, i.e. Not change the proportion of the population that have any of these certain characteristics, we have to make sure that our sample is small enough that it doesn't affect those. So the small enough is always 5%. So big N being greater than or equal to 20, N just means that our sample size is less than or equal to 5% of the population size. And as with the goodness of fit, we have to make sure that the expected counts for each category are at least 5. Big difference here is, instead of just having, one row of expected counts, we have an entire matrix full of expected counts. So we have to calculate a lot of expected counts here. Well, how do we do that? Well, before, the expected count was simple. We just took the proportion that was going to be in that category and multiplied it by our sample size. This calculation is slightly different, and it takes a little bit more work to do, but it's pretty easy to do it in Google Sheets. So let's look at how we can do it in Google Sheets. Okay, so here is our set of data, and we could think of this as the observed stuff, right? This is the observed frequencies. Well, we now need to calculate all of the observed frequencies. So let's go ahead and copy this, just put it down below, and then we'll get rid of all of these numbers. The totals are gonna stay the same, but we're gonna show how to do this in Excel for everything. Okay, so the formula for expected value is, it's going to equal the row sum, so here's my row sum, times my column sum, so there's my column sum, and then divided by the grand total, the sum of everything. So there is my expected value for the first number. And we probably don't need that many decimals for an expected value. In fact, how many do we need here? It looks like 2. So let's bring it down to just 2. There we go. Okay. Now, if we put our cursor in the lower right-hand corner and get the little crosshairs, we can drag it across and then drag it down to replicate that formula. But you'll see that we have all of these errors because Google Sheets and Excel are position-based, right? So when we go to this second cell over, instead of taking U2 times Q, 6, it's taking V2 times Q6, because when we drug it to the right, it's now looking one to the right. And when we come down one row, this first one is still going to be in the U category, right? It's still going to grab the correct row total of U3, but now instead of taking P6, it's trying to get P7. And you'll also notice that it's dividing by U7, this blank right here, rather than U6. There's a nice way in Excel to hold position. And all you have to do is put a $sign in front of positions that you want to be held. And in this case, we want to hold the U column constant, and we want to hold row 6 constant, right? So we need the U's and the 6's to all remain constant. So if we come to our first cell where we did our generic formula, and we say, you know what? Keep U constant. I'm going to put a $sign in front of that. And I want to keep the 6 in the P6 constant, but the 2 can change, right? U2 can then go to U3, U4, and so on and so forth. P can change. It can go from the column P to the column Q, but I always want the total, so I always want 6's. And then I always want to divide by the grand total, so both the U and the 6 need to remain fixed. So that's what the $signs do, is they fix that position. So we're going to fix the U column and the 6th row. And now if we grab the corner and drag again, you'll see that all of those errors are gone. And in fact, because we had formatted the first one to only 2 decimals, they are all only 2 decimals. If you highlight them all and just double click, it'll resize all of them so you can see all of them listed at 2 decimals. Okay, and then if we do some simple sums, right? So equals sum of those. There is that same number, which it should be, right? Drag that down, does all those. Same thing here. We can do equals sum. And it's smart enough to go, hey, you probably want a sum of P9 through P12. And you say, why, yes, I do, Google Sheets. Thank you so much. Hit enter. There's my sum. And drag that over, and there's all of those. Now for these, of course, we don't need 2 decimals. Same thing for these. We don't need 2 decimals because they're whole numbers. And then the grand total, yes, I could have just summed this column or I could have summed this row. But let me point out this neat feature. We can do equals sum, and then we can do the entire table, P9 to T12, and sum that up. And again, we don't need extra decimals. And so all of these numbers are matching all of those numbers. Yay, everything is as it should be. Maybe just to help these kind of stand out, we can make them bold. Oops. Same thing here. Make these bold. So we just kind of, our eye can go, all right, these are all, somehow different. They aren't numbers. They are these totals. Okay, so we've now done observed, and these are now expected. These are the expected frequencies. Now we need to calculate the bits and pieces of the chi-square. We're basically going to compute the same kind of chi-square thing, but for each of these cells. So I'm going to copy this again. And for those of you that are wondering, no, there isn't, like you can't go to any of these extensions like the Excel analysis tool pack and do a chi-square test of a contingency table, kind of a direct, easy way. You kind of have to do it with these computations. Okay, so these are going to be our chi-square values. You don't have to do this. I'm just so you can see. And then this is all going to change. Okay, how do we calculate these? Well, we're just recreating this same formula of the difference between observed and expected squared divided by expected. So it's going to equal the observed frequency. Oop, I forgot my parentheses. Let's just start over. Parentheses, observed minus expected, close parentheses, caret 2 for raising the power, forward slash for division, divide by expected, hit enter. Let's drag again across and down. And the nice thing is because we held everything constant, it's still got the right pattern, right? P3 and P10. So there's P3, and here is P10, and so on and so forth. Because we have our two tables set up nicely, we don't have to worry about changing stuff. This will just do the pattern correctly if you drag in both directions. And we can verify that by these numbers down here. No, we can't, because these are chi-square numbers. They have nothing to do with those numbers up there. So we can, in fact, just delete these and just know that we are correct. This is our chi-square value, which is a pretty big value, right? And that's totally fine. But that's the only one we need. This is our chi-squared value. Okay, so let's go back to this question. We can see 1155325, 561218. There's our 1155325, 561218, right? So all of those seem to be right. Let's just check the last one. 548617. There's 548617. Okay. Then are all the values greater than 5? Heck yeah, they're all huge. No n is given, so we just assume that n is greater than or equal to, and then this is just our sample size times 20. So that would be this grand total, right, of 130,281. Conditions are all met, so we can do a chi-square independence test, right? We're not doing the chi-square goodness of fit, we're doing an independence test. Then our calculations. So here is observed minus expected squared divided by expected, and then here's the last one, right? So the last cell, the observed, expected, and expected. So these numbers are the numbers we would have had here. Right? I'll put it all on the page. So there's that number for expected. Observed is just this one, right? Just like this is going to be the observed for the last one. So this is where we get all those numbers. And then here's our big old chi-square that we got, right? 24070.29. 24070. Oh, we need a couple extra. So 1, 2, there's the 0.29. All right, so we can get the chi-square out of Google Sheets. Now we have to do the p-value. Well, I mean, before we even compute anything, we should know that's so big that our p-value is going to be 0. But we can, do everything with the same formulas that we did for just the chi-square goodness of fit. What was our significance level on this one? It was 1%. All right, so I'll go back down. And 1%. So we'll put in 1%, 0.01. Our degrees of freedom. Now, degrees of freedom is a simple concept, and it's very easy to compute by hand. It's just not easy to have Google Sheets do for us. And the degrees of freedom is just the number of columns minus 1 times the number of rows minus 1. So it's basically how many categories we have for each of our two variables minus 1, and then multiplied together. So for instance, here we have 1, 2, 3, 4, 5, right? We have 5 categories of age. So 5 minus 1 is 4. And then we have 1, 2, 3, 4, 4 different levels or categories for schooling, amount of school. So 4 minus 1 is 3, right? 5 minus 1 is 4. So 4 times 3, our degrees of freedom is 12. So again, it's number of rows minus 1. So here's 5 minus 1 is 4. Sorry, that's number of columns. And then number of rows, 4 of those, minus 1 is 3. So 3 times 4 is 12. Okay, our test statistic is the chi-square that we calculated. So that just equals this value here. I'm just putting everything in like one easy to see place. Now the p-value, that's what we calculated before in the goodness of fit over here, right, with the chi-square distribution right tail test. Same exact thing we're doing here. So equals chi-square dot distribution right tail test. It wants the x value, i.e. our test statistic, comma, degrees of freedom. So there's our 12. There's our p-value, really, really small, right? We can show a few more decimals, but it's not going to change anything. And then if we need to know the critical value, if we're doing the whole, let's compare our test statistic to the critical value test, this is where we can do the inverse test to get back to our critical value based on the significance level. And this is the same formula that we use to get our test statistic kind of the easy way before, but we couldn't really do that here because we don't have a chi-square test to just do. Well, I guess we probably could with just highlighting all of the observed and all of the expected. It might actually do that in a table. I'll have to try that some other time. But for now, if we want to do the critical value, it's just we're going to do the chi-square inverse on our significance level. So we would do equals chi-square inverse right tail test, right? And the probability is the 1, comma, degrees of freedom. And there's the chi-square that we would need to be bigger than. We'd have to be bigger than 26 point something, and we're at, what, 24,000. So that's why our p-value is just a bunch of zeros. I mean, we'd have to probably put 20 zeros out there before we would see something other than a 0. Okay, so test statistic, we already have. Our p-value, of course, is going to be 0. Since the p-value is less than or equal to 1%, we reject. Every time we reject, there is significant evidence to conclude that the two variables, so education and age group, are dependent for all adults. So remember, the null is that they're independent, there's no influence, and then if we reject, then that's saying that there is some sort of dependence, which in essence is just saying your age group is going to have some influence on how much education you got. And it's kind of a no-duh thing, but that's how this test works. Hope that helps.